In this experiment, we'll be investigating how lateral forces such as wind or seismic activity can cause oscillation in structures. By applying different forces to these models with varying masses, we'll observe how these forces influence the structure's motion and stability. The key concepts that we'll be covering are oscillation, which refers to the back and forth motion of a building or object under external forces. And on top of that, we're also going to be talking about the center of mass, which obviously plays a crucial role in how these forces are distributed within the structure, ultimately determining its stability. Through testing these different mass configurations and analyzing their impact on the oscillation, we aim to better understand how mass distribution and force application influences the behavior of structures under dynamic loads.
To build our oscillation model, we use the following materials and equipment: a flathead screwdriver, a drill, some pliers, an electric saw, and table saw, 10 90-degree angles brackets with their screws, 5 screws with their nuts, 6 hacksaw blades or saw blades, wood glue, a wooden plank or board, and modeling plate. First, we cut a section of the wooden plank to cut it into 4 equal pieces, which we glued with the wood glue to the bottom of the board. This was done to make our base a little taller. Note that this step is only necessary if your wooden board is very thin. Next, we cut out one of the hacksaw blades with the electric saw to divide it into short sections. Then we screw the angles onto the wooden board using the hacksaw blades as a gate by placing it in the next 2 angle brackets to know how much space to leave. After that, we align the hacksaw blades with the holes in the angles to pass the bolt screw through them and tighten it on the other side with the nut. Lastly, we mold a sphere with half of a bar of modeling clay and put it at the top of our sauce. And that's how we made our oscillation model.
Another factor to consider when it comes to the rigidity is also the location of the mass itself. As we saw in the videos, the importance of the rigidity is also based on the location of the center of mass. Low structures, buildings such as small houses, have their center of mass very low. This means that the rigidity necessary to counteract that center of mass, well, it's very rigid since it's very small. On the other hand, as in the case of a tall building, the center of mass was at the top, and the rigidity necessary to counteract the movement of that center of mass has to be very high. That's why we can say that the tall structure had a low resistance, had a low rigidity.
Okay, this is trial 2 of the challenge, and we're going to apply a lot of force to the model to generate oscillation. So this ball, the medium one. The ball's movement was triggered by a small push, causing it to swing back and forth. The oscillation was measured at 60 centimeters from side to side and 8 centimeters from the side to the center. And the ball took approximately 0.2 seconds to travel from one side to the other, completing a full cycle. Now, regarding the amplitude of the movement, it was 8 centimeters from the center to the extreme position of each side. If we scale this down to 110, the amplitude of the movement would be reduced proportionally to 0.8 centimeters. Finally, the time it took to complete one cycle at the beginning of the movement was 0.2 seconds, which means he had a frequency of 5 oscillations per second, or 5 hertz. This demonstrates how mass and force application impact the oscillation dynamics and how smaller systems can show similar patterns to a larger scale structures in engineering.
Okay, I'll be explaining the current data of the small ball here right now, and for this one, the total lateral oscillation is 8.5 centimeters, amplitude of 4.25 centimeters, and time for one cycle of 2 seconds. To answer the question of process carried to generate lateral movement that makes the building oscillate, is that the oscillation is produced by pushing the model sideways with a quick force and then releasing it. This small displacement caused restoring force that pulled the model back and forth. It swings from side to side, but once released, it continues oscillating naturally due to elasticity. So rather than just pushing it softly for the small ones, we do we give a quick force and then we make it swing back and forth. So for the second question, what is the amplitude of the movement? Like I said, currently the amplitude is 4.25 centimeters. And third question of if a building was at 1/10 scale, what would be the amplitude of the movement? Since the current scaled amplitude is 4.25 centimeters, we multiply that by 10 and we get 42.5 centimeters for the amplitude. And how long did it take to complete one cycle, the beginning of the movement? Like I said, it took, for one full cycle, it took about 2 seconds.
This is the fourth test we're going to analyze on an Odent high-rise model. This 31 centimeter structure, topped with an 80 grams mass, is designed to show its inherent response to motion. To give you an idea, I will first show you the natural movement of each of the masses, like this one. Similarly, for the next text, I will also demonstrate what the natural oscillatory movement will be like, but with a shock absorber. We first apply a lateral shake to stimulate an earthquake like this one. Due to the inertia, the top masses resist, forcing the structure to oscillate in its natural period. This is the time it takes to complete one full cycle. For this model, the cycle back and forth took exactly about 0.3 seconds. This short period makes it very sensitive to common seismic frequencies. At the peak of its swing, the lateral displacement or amplitude reached about 15.5 centimeters. This displacement is critical. If our model were on a 1:10 scale representation of a real building, that 15.5 centimeters movement will translate to a significant 1.555 meter away in the full scale structure. Test 4 clearly shows the uncontrolled natural vibration that engineers must manage. We now move to test 5, featuring the same structure but with a little piece of paper that will work as our damping system to dissipate vibrational energy. This type of system is designed to control the building's response compared to the uncontrolled motion of test 4. Before we start, this is a natural motion of the building with the damping system. When the lateral shakes begins, observe how the damping system changes the structure's behavior. Look. Instead of a quick 0.3 second cycle, this model takes 0.7 seconds to complete one full cycle. The damping has forced a much longer natural period. This recorded amplitude for the dampest test is 36 centimeters. While the movement is visually larger, the damping system effectively lies in its ability to dissipate energy over a longer time. The goal is not just to reduce the swing, but to prevent the dangerous rapid energy buildup that leads to structural failure. Test 5 demonstrates how engineers use advanced systems to make high rises safer.
The second to last experiment we will focus again on the highest building, but this time it has two masses. Both masses are 90 grams, one located at 32 centimeters and the second one at 16 centimeters. To analyze, we first need to locate its normal frequency. This time, the amplitude changed from 16.25 to 20 centimeters, and the period increased from 1 second to 1.2 seconds. This means it has low frequency, or better said, a lower frequency than before. My thought process was, since we added a second ball, the center mass of the structure would be lower. But practically speaking, the amplitude increased and the period also increased. This meant a lower frequency than before. Now thinking about it, it makes sense. This is caused by the limit of elasticity from the sublet. The force exerted towards the pendulum is higher than before. This meant a lower increase in amplitude, but also meant a longer time to make it back. This is an example of the pendulum. And now talking about a scale of 1 to 10, the amplitude would increase from 162 to 200 centimeters. Another factor to consider when it comes to the rigidity is also the location of the mass itself. As we saw in the videos, the importance of the rigidity is also based on the location of the center of mass. Low structures, buildings such as small houses, have their center of mass very low. This means that the rigidity necessary to counteract that center of mass, well, it's very rigid since it's very small. On the other hand, as in the case of a tall building, the center of mass was at the top, and the rigidity necessary to counteract the movement of that center of mass has to be very high. That's why we can say that the tall structure had a low resistance, had a low rigidity.
Now I will give out my conclusions. So what differences can you see between each of the tests is the first question. So basically each test showed different levels of movement depending on the height, mass, and the damping of the building model. The taller buildings tended to sway more and had a longer period, while the smaller ones moved faster with smaller oscillations. Adding more mass made the buildings move slower, and with larger bending, while removing mass made them react quicker. When damping was added, the oscillation decreased much faster, and the building stopped moving sooner. Overall, each structure behaved differently because its stiffness, mass distribution, and height, they were not the same. And how do we relate amplitude and frequency? Does greater amplitude mean greater or lower frequency? So amplitude and frequency do not directly increase or decrease together. In our experiment, when the amplitude was larger, the frequency did not automatically become higher. The frequency mainly depended on the stiffness and the mass of the building, not on how far it moved. For example, when a tall building, a ball with a big amplitude, still had a slow frequency because it was more flexible. A small building could have a small amplitude but at a fast frequency. So greater amplitude does not mean greater frequency. Frequency stayed almost the same even if we pushed the building harder. Only the size of the movement changed.
The importance of the overall rigidity of the structure means how the frequency is going to be. If it has a high rigidity, such as small buildings, the frequency will be very high. But if the rigidity is very low, the frequency is going to be very high, such as we saw in the case of the tall building. As an architect or as a civil engineer, it's very important to create very rigid structures. This is because low frequency waves are a lot more common than high frequency ones. So if we make our structures very rigid, it's going to be very difficult for it to get damaged in general. Another factor to consider when it comes to the rigidity is also the location of the mass itself. As we saw in the videos, the importance of the rigidity is also based on the location of the center of mass. Low structures, buildings such as small houses, have their center of mass very low. This means that the rigidity necessary to counteract that center of mass, it's very rigid since it's very small. On the other hand, as in the case of a tall building, the center of mass was at the top, and the rigidity necessary to counteract the movement of that center of mass has to be very high. That's why we can say that the tall structure had a low resistance, had a low rigidity. Now, how could we solve this problem? Well, even though the tall building had a very low rigidity, if we lower the center of mass to the center or all the way to a lower point, the necessary rigidity to counteract that center of mass would be less. And thus, if we put the center of mass from tall building all the way at the bottom or even at the middle part, the rigidity of the structure would be very high. Thus, low frequency waves would not affect it as much as it used to.